The wave number and the angular frequency are intrinsic properties of a wave. But what do they represent from a mathematical and physical standpoint? First, let's start off with the equation of a traveling wave. So we have a function psi that depends on the horizontal position. So here we're only looking in one dimension. So x, and also on time, because a traveling wave moves both in space and time. So it is a multivariable function. And it has an amplitude a times the cosine or the sine of kx, where k is the wave number minus omega t, or omega is the angular frequency, plus a phase shift that represents the value or the amplitude of psi at x equal to 0 and t equals to 0. And therefore phi describes the initial state of our traveling wave. And so this is an example of the equation of a wave. And what does psi represent? Well, obviously it depends on the context. For example, if we're looking at a traveling wave on a string, well then psi represents the vertical displacement, y. Or for instance, if we're looking at acoustic waves, can represent the pressure at position x and at time t, because sound, for example, depends on pressure variation. And therefore, psi represents a physical quantity, well, the amplitude of a physical quantity, which varies depending on the context, on the type of wave we're actually looking at. In order to get a grasp of the concepts of wave number and angular frequency, it's important to visualize the psi function. Since it's a multivariable function, it would be difficult to visualize on a plane, a three-dimensional space. And so I've drawn out two graphs for both the x independent variable and time independent variable. One of the most important properties of pure sinusoidal waves like this one is that it repeats itself after a cycle. And this pattern that is associated with waves is what we call the period. And in particular, one property about the cosine and sine function is that it is 2 pi periodic. In other words, it repeats itself after the input has varied by 2 pi radians. Now, in general, traveling waves don't have a period of 2 pi, yet they are periodic, especially when we're considering sinusoidal waves. And our goal here is to determine the period for each independent variable. When we are analyzing waves from a spatial standpoint, we define the wavelength as being the distance between two maxima. And in general, we consider the wavelength as being the distance between two similar occurrences. So when the function has the same value and has the same slope at that point. And therefore, after we have traveled a distance of lambda, the wavelength, the value of our function remains the same. And therefore, from a spatial standpoint, our function psi has a period of lambda when we are considering the independent variable as being x, the horizontal displacement. Similarly, we have a time period, which we denote as capital T. And so after a time capital T, our function resets. It has the same value. And so let's describe what we have just seen from a mathematical standpoint. So we know that our function psi has a spatial period of lambda, and therefore, as we travel a distance lambda, our function resets. So psi of x plus lambda times t should be equal to psi of x and t, because our function needs to reset after a distance lambda, and hence we have this equality, which means that a cosine of k times the input, but the input here is x plus lambda, because we have traveled the distance of lambda from our initial point. So k of x plus lambda minus omega t plus phi needs to be equal to a cosine of kx minus omega t plus phi. Simplifying our expression, we get that a times cosine of kx minus omega t plus phi plus k lambda is equal to the expression that we had on the right. But the thing is, we know that cosine is 2 pi periodic, so it repeats itself after 2 pi radians, and therefore cosine of, let's say, x plus 2 pi is equal to cosine of x. And therefore, the only way for this equality to hold is if k lambda is equal to 2 pi, or more generally, a multiple of 2 pi. But from a physical standpoint, we're only considering the case of 2 pi. And this means that k is equal to 2 pi over lambda. And therefore, from this equation, we can understand that the wave number represents the number of cycles per unit distance. It is measured in units of radians per unit distance because it is inversely proportional to the wavelength, which is measured in meters. And we can clearly understand why that is the case. For example, imagine we have traveled a distance x is equal to lambda. Well, we would have k times lambda, which means that the input here is 2 pi, and therefore the function resets. And this is clearly what we wanted initially. We wanted our function to reset after a distance lambda. And that is why k is the number of radians per unit length. Likewise, we use the same reasoning when it comes to the angular frequency, and therefore the time period capital T. We know that after a time capital T, our sinusoidal wave repeats itself, it resets, and therefore we have that psi of x and t plus capital T, our time period, is equal to, well, psi of x and t. And therefore, we have that a times the cosine of kx minus omega, but now the input is t plus capital T, so omega t plus capital T plus phi is equal to a cosine of kx minus omega t plus phi. And therefore, we have that omega times capital T is equal to 2 pi. Here we're not considering the fact that there's a minus sign because physically it only means that it travels in a different direction. And therefore, omega is 2 pi divided by our time period, which means that the angular frequency is the number of radians per unit time. Now, say we wanted to compute the speed of the wave crests, so the speed of the wave. Well, we know that after a time capital T, the time period, the wave has traveled by a distance lambda. Now, it's important to specify that this is only the case for ideal sinusoidal waves. But nevertheless, we get that the speed of the wave crest is equal to lambda over capital T. And now we can use the formulas that we derived over here to deduce that we have 2 pi over lambda, the whole thing divided by 2 pi over omega, and hence the speed of the wave crest is omega over k. And therefore, to conclude, the wave number and the angular frequency are linked to the periodic property of pure sinusoidal waves. And they describe the number of cycles the wave has traversed per unit length or per unit time.